So the constant is the term in descending order, the term that does not have a variable attached to it. All right. We tend to look at a trinomial as following the form of ax squared plus bx plus c. So we'll often refer to this as the c value. All right. So you just kind of keep that in mind. Like whenever I say the c value, that's what I'm talking about. C for constant, maybe. All right. But it's just whatever that lone term is at the end of an expression. All right. Assuming that it's an appropriate trinomial form in descending order, then it's going to have that relationship. Now, this is kind of a weird aspect to it that gets often overlooked. I say ax squared plus bx plus c. It really doesn't necessarily have to be ax to the second power, bx to the first power. It just has to have the form where whatever the first power is it's going to be double the second power. So you could have, in a more general form, I could say ax to the sixth plus bx to the third plus c, right? But if I want to keep it general, then what I would say is, you're going to love this, ax to the nth plus bx to the n over 2 plus c, where n is a whole number. Greater than 0. All right? So a whole number greater than 0. So I could have ax to the 10th plus bx to the 5th plus c. All right? So just imagine the same expression that we have here in number 5 for some reason. Just with a power of, let's say, 16 and 8. X to the 16th power. 8x to the 8th power plus 7. All right, the technique that I'm about to go over will work for those more complicated expressions also. All right, so what we're going to look at, again, that c value, that constant value, we're going to look at the factors of it. All right, any values that would multiply to give us that number. All right. Now, in most cases, those are going to be whole numbers, but sometimes they can be fractions, they could be decimals, they could be irrational numbers. But we'll start off simple. We'll start off with the case where they're whole numbers or integers. All right. So we're looking for the factors of 7. All right. And once we come up with that list, each factor pair is going to be tested to see if it'll actually add to whatever the b value is. All right? Factors of 7 that add to 8. All right? So I'll look at my factors of 7. It's prime numbers, so it's pretty straightforward. I mean, what are our possibilities? We got 1 and 7, or maybe, it's positive 7, so if we're going to involve negative numbers, maybe it's -1, -7, right? So we could say 1 and 7, or -1 and -7. All right. So out of the possible pairings, I'm looking for the values that'll add to whatever the b value is. All right? So 1 and 7, -1, -7. Which one adds to 8? It's the 1 and 7. All right? So when we're writing the factors here, we have to keep in mind that it's going to be a product of binomials. Right? Just thinking back, and it's like, how do you know that? Well, thinking back to the last unit, when we distributed out a product of two binomials, the result was a trinomial. So if I had something like x plus 2 and x minus 3, distributed out, we ended up with a trinomial as a result. Right? So we're going the other way, assuming that we're going to have two binomials. If we're reversing the distributive property, we're looking at values that have to multiply. If I'm carrying out the double distributing process, just kind of based off of this shell here, I'm going to have a term here and a term here. When I multiply them, the result is going to be that x squared. Then I'm going to take that first term and multiply it by whatever the second term is in the second binomial. I'm going to take that second term in the first binomial, I'm going to multiply it by the first one and the second one, and then distribute it all out, clean it up, simplify, and eventually we get the x squared plus 8x plus 7. All right? But just going back to the very first step, it would be take this number, multiply it by this number to get this number. Okay? The most likely way that's going to play out is if they're both x's. I mean, it's possible that one could be an x squared and the other could be a 1, but that's typically not how it works out. So then you go through the process, you distribute the x against the first term in the second binomial, the x against the second term in the second binomial.
Can I have a package?
Yeah, top of the file cabinet back there. The second term in the first binomial multiplied by the first and second terms in the second binomial. It was basically every part of each binomial multiplied by every part of each other binomial. All right, all that's well and good. But in that process, I'll call them the outer and inner terms, because I mean, we don't really refer to the FOIL method, but first, outer, inner, last. But when you distribute, you end up with a bunch of different products that you combine, and two of them actually combine to give you the middle term. But when you take the x and multiply it by the x, it gives you the x squared. Right? Then you do some other computations and you get the middle stuff. The very last computation that you do is this number multiplied by whatever this number is. And that gives you whatever the constant is in the trinomial. All right? So I look at this and I say, all right, well, that's where the 1 and 7 is going to come into play. All right? So I would say here, 1 and 7, or the other way around, it doesn't matter, because everything's positive. You know, it's going to be plus 1 plus 7 or plus 7 plus 1. It's the same deal. All right? So then all I'd have to do is just test it, check it out, make sure that everything is the way it ought to be, and we should have our set of factors. All right? So I would have x by x, which gives me x squared, x by 7, which gives me a 7x, 1 by x, which gives me a 1x, and 1 by 7, which gives me a 7. I'm just checking to see if this expression here matches what we started with. If it does, then we're good. If it doesn't, then back to the drawing board. All right? So we're looking at x squared plus 8x plus 7. It checks out. So these would be our factors, the appropriate set of factors. All right? It's really just a matter of, I mean, it's an awful lot of number sense, but there is an element of trial and error that comes into play, which I'm going to talk to you about in a minute. But yeah, that's the overall structure. So it's like, well, I think it's 1 and 7. Why? Because 1 times 7 gives me the 7. 1 plus 7 gives me the 8. All right. So looking at number 7, for example, I'd be looking for factors of negative 90 that add well, it's whatever the b value is. In front of that m there is an understood 1, so I'm looking for factors of negative 90 that add to 1. All right, so I'd look at my negative 90 and say, all right, well, what are two numbers that multiply to negative 90? Well, the obvious pairing is 10 times 9. It's just one of them has to be negative, right? Because two negatives will give you a positive product. Two positives will also give you a positive product. But if you mix and match negative versus positive, that's where you get a negative result. So we're looking at negative 10, positive 9, or 10 and negative 9. But then you also have other possibilities. 45 and 2, 30 and 3. Right? There's a bunch of different ways to get to 90. Right? So you start off with a possible pairing, take a look, and say, that's what I was talking about with the trial and error. You start off with a possible pairing, see if you have a winner, and then go from there. All right. So I look at this pairing, or these possible pairings, and I say, all right, these two numbers, these two sets of numbers that I have here, if I add them, will I get a positive 1? Negative 10, positive 9. Well, if I add those two numbers, I'm going to get a negative 1. Positive 10, negative 9. If I add those two numbers, I will get a positive 1. So I have my winner. All right? So then it's really just a matter of saying I have an x and an x, in this case, m. An m and an m. The other two values, there's always a positive built into the expression, so you'd say plus plus. The other two values will be whatever the winning pair is. So I'd look at it and say, all right, well, this one didn't work out. And if neither of them work out, then I move on to other factors. All right, so I have to have a suspicion. I have to look at it and say, well, what's the most likely outcome here? You don't even know. It could be 90 and 1. 90 times 1 is 90. It all depends on what that middle number is, right? So you start off with what you suspect to be the correct value or pairing, try it out, and if it doesn't work, then you go back to the drawing board. All right, so here I'm going to put in a 10 and then a negative 9, plus minus, that's, you could skip that step if you want, but it would just be m minus 9, right? So m plus 10, m minus 9, all right? And you could distribute the whole thing out to verify that it's going to give you this expression here, but I like to use a different method of the name of which is kind of a work in progress. Call it the rainbow method. So when you arrive at what you suspect is the correct answer, instead of distributing out the whole thing, that could take a little while. Maybe honestly, it probably doesn't take that long. The issue that you run into is, what if you make a mistake when you're checking, which casts doubt on your original answer, which was correct, but because you made a mistake in checking it, now you think your correct answer is incorrect. All right? So we want to streamline this as much as possible. All right? So what we would normally do is multiply the first value by each of the two terms in the second expression, then multiply the second value, same deal, by each of the two terms in the second expression. But we already know that multiplying the first values, that's going to give us the m squared. That's why we put the m and the m there to begin with. We already know that the 10 and the negative 9 multiplied is going to give you the negative 90, because that's where we came up with those numbers to begin with. The only real concern would be the other computations, which would be the 10 multiplied by the m, the m multiplied by the negative 9. All right. These two products should give you whatever the middle term is. All right. For the last question that we did, it was an 8x. But for this one, it was a 1m. All right. So I'd multiply, just quick check, 10 times m, 10m, m times negative 9, negative 9m, and just have a quick look to see if these two terms add to give you whatever the middle expression or middle term of the expression was, which was a 1m. 10m and negative 9m will add to give you a 1m. So we have a winner. All right? We already suspected that. We came up with that expression to begin with. Bless you. But it's nice to confirm it. So what I do, and this is where the number sense comes into play, is I go right to the pair of binomials. So all this stuff I write about, the factors of negative 9d that add to 1, factors of 7 that add to 8, that's going on upstairs. That's in the mind. All right? So I'd look at number 9 and I'd say, I need factors of 40 that add to negative 13. All right? So then I would look at my expression here. I look at variables k. So now I just kind of play it out. All right, 40. What do we know about 40? Factors 1 and 40. If I add a 1 and 40 together, will I get a 13? No. If I subtract them in any way, 1 minus 40, 40 minus 1, I won't be anywhere near a 13. All right? So that's not a winning combination. 2 and 20, same deal. Add 2 and 20, not going to get a 13. Subtract them in any way possible, not going to get a 13. All right? So you go down your list and you start thinking, all right, well, I'm running out of possible pairings here. 4 and 10. So you think 4 and 10. All right, well, now we're closer. Because this is a positive number, we'd have to be looking at 4 and 10 or negative 4 and negative 10. Adding those values is still not going to get me to a 13 or negative 13. So it's like, oh, we're running out of ideas here. But you keep going down the list and you start thinking, all right, well, what are the other possibilities? Eventually you come across 8 and 5. And you think, all right, well, let's try 8 and 5. Eight times 5 is 40. If I add an 8 to a 5 or a 5 to an 8, I'm going to get a 13, but it's the wrong sign. Now, because I'm multiplying to a positive 40, it could also be the case that I'm looking at a negative 8 and a negative 5. So it took a little while here, but I eventually came up with the winning combination. All right, because negative 8 plus negative 5 will result in a negative 13. All right, so it's k plus. Now you just pop in these values, negative 8, negative 5. Simplify. You skip the part where you have to simplify and just put it in the simplified form. K minus 5, k minus 8, or vice versa. So a natural concern would be, what if you can't come up with the factors? What do we do there? The answer, as it always is, well, not always, but most of the time is, it's Desmos or the TI calculator, whatever you like. All right, so you make a table and look at the set of factors. All right, so in Desmos it's actually pretty easy, but you could do it using the TI calculator also, just not quite as user-friendly. So if you're doing it on Desmos, hit that little plus sign, create a table. You got your x1, y1. Maybe you don't like that. You could use k, just like this problem has k. All right, and so I'm looking for values that multiply to 40, so my second column here would be 40 divided by whatever k is. All right, we don't need the graph. You know, you could look at it if you want, but it's not going to make a difference. So k is our variable. 40 divided by k would be whatever the value, whatever you put in for k, multiplied by whatever results in the second column, should multiply to give you a result of 40. Right? I mean, will multiply to give you a 40. Right? So let's say I put a 1 here, it gives me a 40. It's going to give me the factors. All right? And you're like, oh, okay, well, now I got to type in all these values. That sounds like fun. All right? I hit enter 2. But then it starts auto-populating. All right? So it's like, all right, well, the trade-off there. You type in the first couple of values, and then after that it starts putting in numbers for you. You know, you can keep going, but once you get halfway to the desired number, unless you're willing to live with fractions, and in some cases we'll have to deal with fractions, you're probably already there. All right? But I got out to 40 pretty quickly just by hitting enter a bunch of times. So then what you would do is look across each row and say, all right, well, what would I get if I add these two numbers together? And you're like, well, that's all well and good if the results are positive, but what if they're negative? Well, you do the same thing, but in the negative direction, right? But you can also have Desmos do the sum of these two columns for you. All you'd have to do is take the column headings and add them together. So I would say k plus 40 over k. Trying to get it so that we can see all three columns in one shot. It's not looking good. All right, well, I'll just scroll back and forth. But you kind of see it. Well, at least a second ago you did. There we go.
Wait, how would you do this on like the TI calculator?
I'll get to that next, yeah. So I'd look down my third column and look for that negative 13. The problem is I only have positive numbers here. So then what I would do is throw in some negatives. So I go down to the end of my table here and start going in the negative direction. So negative 1, negative 2, negative 3, and so on, and carry it out that way. But if I look at this, I get to the 8 and 5, for example, and I see that there's a 13, but it's a positive 13, then I would say, oh, well, I got the 13. I just want it to be negative. I wonder what would happen if I made those two numbers negative. Oh, there we are. You know, so sometimes you just learning about the positive sums is enough to get you a handle on the negative sums. All right. Now for the TI, it's not as elegant, but it's still doable, assuming my TI wants to open. Come on. Where are you? Oh, there it is. So in the TI, what you would do is go into y equals to get the factor pairs. You type in really the same general idea as what we did in Desmos. You're just limited to x. You can't use whatever variable you want. So we type in 40 divided by x. And when you go into the table of values, the second graph, it populates a table for you, which is wonderful. So you would look down these two columns and say, all right, well, what would I get if I added these two numbers together, these two numbers together, and so on. Until
40 times x, and like, how do I get to the graph again?
you're going to the table, so you hit second graph. Upper right-hand corner is the graph key. So second, hit that key, it'll bring you to the table.
It says there's an error.
Interesting. I'll have to look at it because sometimes there's a setting. All right. Now, you want the sums too. You don't want to, I mean, I assume anyway. You get the pairings, but you don't want to do the mental math to get the sums. Then you want the calculator to do that for you. All right. So just like Desmos, we need the computation that'll give us that, whatever the result is. All right. So what we're going to do in the next little field here is type in x plus 40 divided by x. All right. So whatever the x value is added to whatever 40 divided by x is, and that would give us the sums that we got in the that third column. Oh, actually, I moved the wrong thing. In that third column on Desmos, all right? So second graph, now we have our sums, all right? The issue with doing it on the TI is that, we're going to need the y equals to create other graphs. So it's not like you can just leave it there. With Desmos, I mean, it's pros and cons either way. Desmos, you could save it and be like, this is how I come up with the numbers for factoring. Like that would be a lengthy title for what you're, for calling your script, but it would be something. The drawback to that is you can't use Desmos on the region. So, there's pros and cons either way. But you just look down your Y2 column here, looking for any instance of a negative 13. And you go both ways, into the positive realm and the negative realm. Oh, there's my negative 13. And then there it is. You're good to go. So with this setup, if you have TI, you would only have to change that 40 into whatever the problem calls for. So in number 11, the relevant value is a 36. So I'd make this 36. Go into my table looking for a 15. All right, in my Y2 column, because I'm looking for two numbers that multiply to 36 but also add to 15. Now this technique, it might be overkill, because you might already come up with it. You look at it and say, well, 12 times 3 is 36, and that also adds to 15. Great. You have the number sense necessary to do all this stuff in your head. Wonderful. We don't all have that yet. All right, so we need something else to fall back on. I see a lot of negative stuff here. I only want positive. So I go into the positive realm. Oh, there it is. There's my 15. So the values I'm looking for are 3 and 12. So my factors would be x plus 3, x plus 12. Or the other way around, x plus 12, x plus 3, because multiplication is commutative. All right? So you see in the first couple of examples, actually in the first example, a lot of detail. Second example, a little bit less. Third one, less. The last one, now it's just like, just do it. Find two numbers that multiply to the C value, the constant value, that also add to whatever the B value is. All right. Now that all changes up when the leading coefficient is something other than 1, but it doesn't change up so substantially to make this technique worthless. All right. So I'd look at this one, number 6, and say, all right, well, we're two numbers that multiply to 24. 6 and 4, 8 and 3, 12 and 2. Oh, 12 and 2. That'll get me to a positive 14. What if they're both negative? So then my suspicion is that I'm looking at negative 12, or negative, well, I'll say negative 2 because I already wrote it. Negative 2, negative 12. Will that pair add to a negative 14? The answer is yes. So x plus negative 2 x plus negative 12. Same idea as x minus 2, x minus 12. For the check, we use the, I don't know, maybe it's better served to call it like the watermelon method. I don't know. I never came up with it. It doesn't really look like much of a rainbow, but like the arc method. I don't know. It's the check. We take the outer terms and multiply them, take the inner terms and multiply them, and make sure that this sum, if I add these two terms together, give me the middle term of the expression. If the answer is yes, then you have your appropriate factors. So number 8 is quicker and quicker every time you do it. Like, all right, well, what are two numbers that multiply to 10? 2 and 5. Right, but that's not going to get you a 9 when you add them together. Negative 2, negative 5, the same deal. Positive 2, negative 5, no. Negative 2, positive 5, no. All right, so I ran through every possibility as it applies to the numbers 2 and 5. So it's not 2 and 5. All right, 20 and 1/2. Well, we're not at fractions yet. All right, so let's think whole numbers. The only other possible pairing would be 1 and 10. All right, so 1 plus 10, 11. No help there. 1 minus 10. All right, so positive 1, negative 10, negative 9. We're on to something here. The idea of the two signs being different. All right, so then you look at it and say, well, how about 10 and negative 1? 10 plus negative 1 would give you a positive 9. So I'm looking at x plus 10, x minus 1. Quick double check. 10x, negative 1x. That gives you a 9x. And we have it. All right, so we have our factor pair. It's like trial and error with intelligence. You know, because we are running through different possibilities, but you start like eliminating the different like absurd cases. Like I wouldn't look at 40 and 1/4 as a possible pairing. All right, because my middle term isn't fractional. All right, if I see my b value as being small, I'm thinking my factors should be pretty close together. If I'm seeing a b value that's large, I'm thinking my factors should be pretty far apart. All right. The problem is when the b value is a middle of the road number, like in number 10. Well, they're not really, it's not really small, it's not really large, so my factors are supposed to be far apart or close together. I don't know. So I run through all the possibilities. 1 and 18, no. 2 and 9, no. How do I dismiss those so quickly? Well, because I'm looking at 2 units of difference away from a 9. All right, so if I'm using a baseline of 9, and I go 2 steps in any direction from 9. I get up to an 11, I get down to a 7, I'll never get down to a negative 3. Even if I'm using negative numbers, never going to get to a negative 3. All right, 18 and 1, start off with your baseline of 18, increase, decrease by 1, never going to get to a negative 3. All right, so then I get to 6 and 3. Look at that possible pairing. And I'm like, all right, well, if I use a baseline of 6 and increase, decrease by 3, I'll get to a positive 3 and a positive 9. Well, I want them to be negative. So maybe I don't start with a positive 6 as my baseline. Maybe I start with a positive 3 as my baseline. Use that and say, all right, if I increase and decrease by 6, I get to a 9, I get to a negative 3. All right, so it's a plus minus situation. I start off with the 3 and I say, all right, well, if I increase by 6, will that get me to a negative 3? No. If I decrease by 6, will it get me to a negative 3? Yes. So I'm looking at decreasing by 6, starting with a positive 3, And if none of that worked, I would say, all right, well, what if I start with a -6 and increase, decrease by 3? Start off with a -3, increase and decrease by 6. You got to run through the possibilities if you don't have a thought. All right? But if you do have a thought, then you can streamline the process substantially. All right? So in this one, if I was really at a loss, I'd go to my calculator. I'd say, all right, well, let's get a -18 in there. Go to my table and look for a -3. Oh, there it is. Although I think I typed it in wrong. Yep. I was like, where did that 54 come from? Yeah, there it is, -3. So 3 and -6 would be my winning combination. All right. So number 12, I'm looking at numbers that multiply to 48, -48, but they'd have to be pretty close together in order to have a difference of 2. All right, difference of 2, whether it's positive or negative, is immaterial at this point. It's a difference of 2. Look at the absolute. All right, so two numbers that are only 2 units apart that multiply to 48. 6 and 8. You know, it goes back to like 3rd grade when they're like, well, you got to know this multiplication table. And you're like, why? I got to just use a calculator for moments like these, because then you can say, well, what are my possibilities without having to crunch every single thing? You know, you still have the option to crunch every single thing, but knowing how to, just kind of run through it in your mind is pretty useful. All right, so I'm looking at 6 and 8. All right, so am I increasing the 6 by 8? No, that wouldn't make sense. That's going to get me to a 14. Am I decreasing the 6 by an 8? Yeah, that'll get me to a -2. So x plus 6, x minus 8.